these calculus videos, written and performed by me, Patty Leitner.
Part 4. Integrals. Section 5.3. The fundamental theorem of calculus and the definite integral.
Lesson 3. The geometry of the definite integral. Part 1. Okay, let's go ahead and look at the next page. And what we'll be doing for the rest of this section is expanding our idea of the definite integral. So we are going to continue to assume that we have a function little f that is continuous on the interval from a to b. And we saw in the previous example how important it is for our function to be continuous on the interval that we're going to integrate over. But remember what we've said so far is that the definite integral from a to b of little f of x dx is equal to capital F of b minus capital F of a, where remember capital F of x is an antiderivative of little f of x. Normally, of course, we have steps in between these two sides. This is our ultimate definition, but normally if I'm integrating from a to b little f of x dx, remember the steps we take is first we find an antiderivative of little f, that gives me capital F of x, and then I evaluate that at my limits of integration. So I always plug in the upper limit first, capital F of b, and then plug in the lower limit, capital F of a, and I subtract those two. So that's our definition of the definite integral, but so far we've kept insisting that the function little f of x that's in here, that we're integrating, be above or at worst on the x-axis on the interval we're integrating over from a to b. So we had to have a black curve like this that was above the x-axis or maybe touched it, but did not go below the x-axis on that interval from a to b. And I promised you earlier that we would talk about what happens if we have a function that goes below the x-axis. And that's the part of the lesson that we're getting into. Well, we said in the case that the curve is above the x-axis, or at worst on the x-axis, this definite integral represents the area underneath the curve from a up to b. It represents this green area. But what we want to ask now, what we want to investigate, is what would happen if my function little f is below or partly below the x-axis on this interval from a to b. And over here on the right I have a couple of pictures showing the different possible scenarios. F is still continuous, so it doesn't have any breaks between a and b. But you notice in this picture here that y equal f of x is actually below the x-axis everywhere on the interval from a to b. And we haven't talked about what the definite integral means in that case. And in this picture down here, we have a function y equal f of x that is partly above and then crosses the x-axis and is partly below the x-axis on the interval from a to b. And we have not considered that type of function either. So here's our big question for this last portion of section 5.3. We could still compute the definite integral from a to b of f of x dx no matter what the graph looks like, whether it's above or below or partly above and partly below. And as long as you can find an antiderivative of little f and you can figure out what the antiderivative is, you could certainly find that antiderivative and plug in your limits and say, oh, well, I'm going to compute capital F of b and I'm going to subtract capital F of a, and you'll get some number. I'll put some number as an answer. So as long as you can find an antiderivative of little f, you can compute this integral. There's no problem doing it. But the question is, what does this number that you end up with represent graphically? We said in the case that the function is above the x-axis, it represents the area underneath the curve. But does it still represent the area, say, between the curve and the x-axis if the function is below the x-axis on the interval from a to b? Or if it crosses somewhere in between, does this number represent the total area between the curve and the x-axis? We don't really know. We haven't talked about that. And when we proved the fundamental theorem of calculus with our little picture proof, which by the way could be made more rigorous by using the mean value theorem, we considered only this type of picture where the function was above or on the x-axis. We didn't consider these, so we don't know yet what this definite integral represents in these types of cases. Let me give you a specific example so that you can understand exactly the question that I'm asking. And I sort of restated this starred, red starred question for this specific example. Suppose I have the integral from -1 to 2 of x cubed dx. And you remember what the x cubed graph looks like. It's something like this. I graphed a portion of it here for us. We are integrating from -1 to +2, and you notice that for part of that interval from -1 to 2, the curve is below the x-axis, it crosses at 0, and then it's above the x-axis for the other portion of that interval that we're integrating over. So let's go ahead and actually do this problem, and then later we're going to come back to it and try to answer this question that I have down here about it. Well, if I were just to dive in and do this problem, I do notice that x cubed is a polynomial, so at least it's continuous everywhere, and so in particular it's continuous on this interval from -1 to 2. So we won't fall into that problem that that student had with the function 1 over x squared that was not continuous at x equals 0. So I can go ahead and find the antiderivative of x cubed. That would be 1/4 x to the 4th. And I can certainly evaluate that from -1 to 2. And so I'm going to do 1/4 times 2 to the 4th minus 1/4 times -1 to the 4th. And let's see, it looks like I'll get 16 over 4. That would be 4 minus 1/4. So I get 3 3/4 if I want to write it as a mixed number, or I guess I could write that as 15/4 if I want to write it as an improper fraction. But the question is, what does this number represent graphically? And I put in parentheses, is it the total area between our black curve and the x-axis? So we don't know. We get the number 15/4, but is that this total area? We're not sure, and that's what we want to answer. Now, notice here when I put my answer, it isn't really an answer. It just says to answer this, we first need some properties of definite integrals. So we're going to come back to this starred question, both for this example and for functions little f of x in general. But first we need a few properties of definite integrals. So we'll come back to this starred answer very shortly. So let's go ahead and look at some properties of definite integrals. And I'm going to continue to assume for these different properties that we're talking about a function f that is continuous on whatever interval of integration we are considering, the interval in general from a to b. Well, let's look at the first property. And what's weird about this integral? I'm asked to do the definite integral from a lower limit of a to an upper limit of a of little f of x dx. So what's weird is that the lower and upper limit are the same number. I drew a little picture over here just to kind of illustrate. Here's a curve y equal f of x, and instead of doing the integral from a up to some larger number b, I'm just doing the integral from a and I'm staying at the same value to a. And so instead of getting sort of a region here, I'm really just getting like a line segment underneath the curve. And what's the area of a line segment? If you want to, you could think of it as a very skinny rectangle that has some height. But what would the width of a line segment be? It would be a width of 0. And so it looks like the area under this curve, the area of a line segment, would be equal to 0. So I'm going to put this down as just sort of a guess here. I'll put guess in parentheses. It looks like the value of this definite integral should be equal to 0. And that does turn out to be true. Let's prove that by just using our definition of our definite integral. When we integrate from a to a, the function f of x dx, well, we just said that the definition of the definite integral, you find an antiderivative. So I find a capital F of x, that's an antiderivative of little f, and I just evaluate that from a to a. And what happens when I do that? Well, I would end up with capital F of the upper limit, which is a, minus capital F of the lower limit, which is also a. And so, yes, I do end up getting 0 as a value for that definite integral. So an example down here, suppose I asked you to integrate x over x squared plus 1, which looks like a hard function to integrate, from 3 to 3. Well, I can automatically say that since my lower limit is the same as my upper limit, this thing should be equal to 0. And there's no point in trying to find the antiderivative of this. In fact, we looked at an integral earlier that had this function in it, and I mentioned that you won't learn how to find the antiderivative until you get to section 5.5, and you need a technique called U-substitution, often abbreviated U-substitution technique, to even find the antiderivative. I'll say to find capital F of x. So we don't even know how to do that yet. You will in a week or so, but right now you don't even know how to do it. But you don't have to know how to do it because we have this property that if the lower limit and the upper limit are the same on a definite integral, the value of that definite integral is 0. Well, let's go ahead and look at the next page and some more properties of definite integrals. So the next property that I have up here at the top, property number 2, you notice what's a little strange about this definite integral is that it is the integral from b to a of little f of x dx rather than the integral from a to b of f of x dx. It turns out that when you swap the upper and lower limits, when you interchange those two, it exactly switches the sign of the definite integral. So the integral from b to a of f of x dx is minus the integral from a to b, where we have these in their normal alphabetical order, of f of x dx. What we say in words is that interchanging the limits, meaning the limits of integration, switches the sign of the definite integral. So in other words, another way of thinking about it is that if you did the integral from b to a of f of x dx, you'd get some number, and you'll get exactly the opposite number if you did the integral with the limits in the opposite order from a to b of f of x dx. Well, I've told you what the answer to this property is, but I haven't proved it to you, so let's prove it, and it's quite easy to prove. We can start with the left-hand side and try to transform it step by step into the right-hand side. So I'm going to start with the integral from b to a of f of x dx. Well, how do I do that? I find an antiderivative, capital F of x, and I evaluate that from b to a. And what does that mean? That means I plug in the upper limit first, so I would do capital F of a minus, and then I evaluate it at the lower limit, capital F of b. Well, I'm going to rewrite this in a slightly different form. I'm going to pull a minus sign out of that expression. I would have minus, and in here I would need a minus capital F of a and a plus capital F of b. And I can see that if I were to distribute this minus sign out, negative times negative would give me a positive capital F of a, and negative times positive would give me a negative f of b. So I've pulled a negative sign out of that expression. Well, let's see why I did that. This thing, if I look inside the parentheses, I could just flip the order of the terms and write capital F of B first and write the minus f of a second. And I want you to think about what this expression inside the parentheses is equal to. Capital F of B minus capital F of A, that's actually just our definition for the definite integral. If you go back a couple of pages where we defined what f of b minus f of a is, when we were defining the definite integral, capital F of b minus capital F of a is the integral from a to b of little f of x dx. So what's inside that parentheses on the right hand side here is exactly the integral from a to b of little f of x dx. So this thing inside the parentheses is exactly the definite integral from a to b of f of x dx. And so we've taken the left-hand side of the thing we were trying to show and step by step shown that it's equal to what I have on the right-hand side. And so that's a nice proof of that property. Okay, well, let's go ahead and look at the next property. That's property number 3. What does it say? I'm doing the integral from a to b of a constant multiple c times f of x dx. And what you might guess I could do with this constant multiple of c, you might guess, and that turns out to be correct, that just like for indefinite integrals, with a definite integral, I can pull that c outside of the integral sign. In other words, the integral from a to b of a constant times f of x is the same as that constant times the integral from a to b of just little f of x dx. Now that's actually a rule that we already proved for indefinite integrals, but this is the constant multiple rule for definite integrals. Well, how do I prove something like that? It's fairly easy to do. We start with the left-hand side, and just like the last proof, I try to show step by step that it's equal to the right-hand side, justifying each step with a reason. So I'm going to start with the left side, integral from a to b of c times f of x dx. And remember that if I were doing this integral, well, how do we do any integral? We start by saying, okay, I have c times f of x, I need to find an antiderivative of that. But we already proved the constant multiple rule for antiderivatives and for indefinite integrals, the set of all antiderivatives. So we have a constant multiple rule for indefinite integrals, and that means that if I were trying to find an antiderivative of this, it would just be c times whatever the antiderivative of little f is, which I'm going to call capital F of x. So I'm going to put down here that as I go from here to here, I'm really using a property of indefinite integrals. So this is by the constant multiple rule for indefinite integrals, which we already proved back in section 4.9. I'll say from section 4.9. So that was something we had previously proved, that you can essentially just carry the constant multiple along. Let's go ahead then and complete this. We've found the antiderivative of this, but now we want to evaluate that from a to b, squish that in there. And so I'm just going to take this function and evaluate it at the upper limit. So I replace x with b, and then I take this function and evaluate it at the lower limit. So I'm going to replace x with a. So now we've done this integral, I'm just going to start rewriting things to try to make it look more and more like the right-hand side that I have over here. So I'm going to pull out the common factor of c. That would be c times the quantity f of b minus f of a. But just like in the last proof, what is capital F of b minus capital F of a? That's just our definition of the definite integral from a to b of f of x dx. So this would be c times, and this thing inside the parentheses is simply the integral from a to b of little f of x dx. And so we've gone from the left-hand side of what we wanted to show step by step to the right-hand side. And so now we have proved that third property of definite integrals. Okay, let's look at the fourth property. This one I think I won't prove. It's done in a very similar way. You'll start with the left-hand side and show step by step that it's equal to the right-hand side. This is the sum rule again for definite integrals. We actually already proved it for indefinite integrals back in that section 4.9. Well, what do you think might be true if I do the definite integral from a to b of a sum of two functions, f of x plus g of x dx? What can I do? Well, just like with indefinite integrals, it turns out that you can do each of these definite integrals separately and add the numbers that you get for answers together. In other words, the integral from a to b of f of x plus g of x dx is the same as the individual integrals a to b of f of x dx and the integral from a to b of g of x dx added together. Remember, we often say the integral of the sum, the definite integral of the sum, is the same as the sum of the individual definite integrals. And when we're more casual, we just say the integral of the sum is the sum of the integrals, just because it has a nice rhythm to it. And the proof, I'll just put, is very similar to the proof for, I'll say proofs for number 2 and 3 above. Basically, all you do is take this left-hand side, write out what you mean by it, use some properties of indefinite integrals to find antiderivatives, rearrange it in a clever way so that you end up with something that's equal to the integral from a to b of f of x dx plus the integral from a to b of g of x dx. And that might be a nice exercise for you to actually try. Okay, let's go ahead and look at the next page. This is the last of our properties of definite integrals that we will need in order to answer that red starred question that I talked about earlier. So here's our last property of definite integrals that we need at this point. We're doing the integral from a to b of some function, f of x dx. Well, what does this property say? It says that if I do the integral from a to some intermediate number, I'll call that c of f of x dx, and I add on the integral from c, that intermediate number, to b of f of x dx, that these two sides are actually equal to each other. So if you want to, think of it in terms of pictures. Here I have a graph of f, and here's the same graph of f. And here's the interval from a to b on this picture. Here's the interval from a to b on this picture. And c is some intermediate point. At least on my picture, it's between the a and the b. And what this property is saying is that if I do the integral all the way from a to b of this function f, it will be exactly the same as if I do the integral from a to the intermediate point c of that function and add on the definite integral from the intermediate point c up to b of that function. Well, let's prove this in general, and then we'll come back and think in terms of the picture about what that really means. So the proof is similar to the proofs that we saw before. What I'm going to do is just actually, in this case, I'm going to take the right-hand side and transform it into the left-hand side. It's a little easier to go in that direction, and that would be fine. So I'm going to start out with the right-hand side, integral from a to c of f of x dx, plus the integral from c to b of f of x dx. And I'm going to try to show step by step that that's the same thing as the right-hand side. When you're doing a proof, oftentimes it's easier to start with the more complicated side and make it look like the simpler side. That doesn't always work, but it's a good first guess. So let's go ahead, and what I'm going to do is write out what I mean by the integral from a to c of f of x dx and what I mean by the integral from c to b of f of x dx. So if I were integrating this first integral, in fact, let me put my equal sign right down here, so it's right underneath. If I integrate this thing, how do I do that? I find an antiderivative of little f, and I get capital F of x, and then I'm going to evaluate that from a to c. And if I want to write out how I would do this second integral, I'm still finding the antiderivative of the same function to the left, so I'm still going to get capital F of x, the same antiderivative, and I'm going to evaluate that from c to b. Well, that means when I plug in my upper limit here, I would start with f of c, and I would subtract the value at the lower limit, f of a. And the same thing for this second integral that I'm doing. I would do f of the upper limit first, so I'd have f of b, and I would subtract the value at the lower limit, f of c. Well, when I look at this long string of terms that are added together, something cancels. Can you see what cancels? The capital F of c here cancels with the minus capital F of c there. Those add up to 0. So what am I left with here? Well, I'm left with a negative f of a and a plus f of b. Let me write the f of b first. It's capital F of b minus, there's a minus sign here, capital F of a. And as we've seen in all of the earlier proofs, what is capital F of b minus capital F of a? That's actually just our definition of the definite integral from a to b of little f of x dx. And notice that this is the right-hand side. So in this case, we started with the left-hand side of the property we were trying to prove, and step by step got to the right-hand side of the property. And so now we've proved that this thing is the same as the sum of these two other integrals. Well, in terms of a picture proof, it's very simple if you're considering a function that's just above the x-axis. But I want you to note that we weren't really assuming that about any of these f's here. We were just assuming that we could find some antiderivative capital F. And also, when I wrote out this proof here, I wasn't really assuming that the c was in between the a and the b. So it turns out that the c does not have to be some intermediate point in between a and b. It can lie outside of that interval, and this proof works just as well. But to understand kind of the concept of this proof, it's easier to assume that your function is above the x-axis and that this c value is somewhere in between the a and the b value. In that particular case, it's very easy to see why this property is true. If f is above the x-axis, then the definite integral from a to b of f of x dx would be exactly equal to this green area that's here. And if I look at these other integrals on the right-hand side, this red portion here from a to c, that would also be an area under the curve, because I know my curve is above the x-axis in this picture. And so the area, that red area, would be the definite integral, not from a to b, sorry about that, but from a to this intermediate point c of f of x dx. So this red area in here would be the integral from a to c of my function. And then when I look at this orange area over here, I'll just write it in purple, the area under the curve from c to b would be the definite integral from c to b of f of x dx. So what I've written down here are definite integrals that represent all of these areas. This green definite integral represents this total area under the curve from a all the way to b. This red definite integral represents the area just from a to c under our curve, and this purple definite integral represents the area just from c up to b underneath our curve. Well, what can I say when I look at the picture about these areas? It certainly looks as if this entire area here would be exactly the same as this red shaded area plus, I'll put a big plus sign here, plus this orange shaded area. In other words, this definite integral, which represents this whole area, should be equal to this definite integral, which is this area, if I add it on to this definite integral, which is this orange shaded area over here. It's really a statement saying that areas add, so the whole area is equal to part of the area plus the other portion of the area. And that's all this property is saying. Okay, so let's go ahead and just do a couple of examples just so that we can get used to these different properties of definite integrals. So I'd like us to look at this example. It's kind of an interesting one. It says, given that the integral from 2 to 7 of f of x dx equals 12, and the integral from 2 to 5 of f of x dx is equal to 9, find, and then they ask us to find a bunch of stuff. Now, what's strange about this particular question is, you notice they don't tell us what little f of x is. They just tell us what the answer to some definite integral problem is. So you have some unknown function, but you do know that if you integrate it from 2 to 7, you'll end up with an answer of 12, and if you integrate it from 2 to 5, you'll end up with an answer of 9. And they ask us to find a bunch of different stuff, integral from 7 to 2 of that function, integral from 7 to 7 of that same function, and an integral from 5 to 7 of that function. And I drew a little picture here. You don't really know what f of x looks like, but sometimes it helps to visualize and understand if you just sort of draw a picture. And here are the different integral limits that come up in various questions, the 2, the 5, and the 7. What I'd like you to do is to pause the video and think about parts A, B, and C, do as many of them as you can, and write down which of the properties of definite integrals that we just proved you used in each of these solutions. Then if you get stuck and you've tried all three of them, go ahead and restart the video and we'll go through them together. Okay, well, let's go ahead and see if we can do some of these together. Let's look at part A. We are doing the integral from 7 to 2 of f of x dx. Notice we are given the integral from 2 to 7 of f of x dx. We're told that that is equal to the number 12. Well, what did we say happens when you switch the limits of integration and switch from 2 to 7 to 7 to 2? Remember, we said that exactly switches the sign of the definite integral. So the integral from 7 to 2 of f of x dx should be exactly minus the integral from 2 to 7 of f of x dx. And which property was that? Let's see, I don't have the numbers memorized, so it's not terribly important, but I think that was property number 2. So if you remember, property 2 said when I switch my limits of integration, it changes the sign of the definite integral. So that was property number 2. So I'm just going to put a little thing here to justify that step. That was property number 2. And we know from what was given up here that the integral from 2 to 7 of f of dx is equal to 12. So we know that this definite integral right here is equal to 12. That was given. And so my answer will just be minus that. My answer would be a minus 12. Switching the limits exactly switches the sign of the definite integral. So it switches whatever, the sign of whatever number equals that definite integral. Okay, how about part B, the integral from 7 to 7 of f of x dx? Well, we're starting and ending at 7. It would be like finding the area under this curve from 7 to 7. It's like finding the area of a line segment. And remember, we said in that case, you always end up getting 0. We don't have to know what the antiderivative of little f of x is, and of course we don't, because we don't know what little f of x is. And this was property number 1. That was the first one that we proved. Okay, well, what about this one? I want the integral from 5 to 7 of f of x dx. Now notice, they do give me the integral from 2 all the way to 7, and they give me the value of the integral from 2 to 5, and I want the integral from 5 to 7. So this looks like we're probably going to be wanting to use property number 5, the last one that we proved. Remember we said that the integral over the entire interval we're talking about, the integral from 2 to 7 of f of x dx, which in my picture you would think of as this whole area under the curve from 2 to 7, should be equal to the integral from 2 to our intermediate point of 5, which would be this area under the curve from 2 to 5 of our function, plus the integral from that intermediate point of 5 up to 7 of our function, which would be this area over here. Essentially, we're saying this whole area from 2 all the way to 7 should be equal to the area from 2 to 5 plus the area from 5 to 7. So if we do these two areas separately, it should be the same as the total green area from 2 all the way to 7. So let's go ahead and see what we know in this equation. We are given the integral from 2 to 7 of f of x dx. We're told that is equal to 12. So this is 12. We are given the integral from 2 to 5 of f of x dx. We're told this is equal to 9. And the thing that we want is what's right here, the integral from 5 to 7 of f of x dx. That's what we were asked to find. And what would that have to be to give us a correct equation? That would have to be the number 3. 9 plus 3 equals 12. Or if you want to, you can solve for this by subtracting this integral from both sides and get 12 minus 9 on the left side. Either way is okay. But the answer to our problem, what this integral has to be, is that missing number of 3. Okay. What I'd like us to do next is to use all of these properties that we talked about to answer that starred question that we asked just a few pages back. Remember I said we needed some properties of integrals to answer our question, and now we have those properties